Hello, my name is John Bozard, and this is my Physics 2211 Lab 4 on spring and mass oscillation. The goal of this experiment is to observe and analyze the motion data of an oscillating mass attached to a spring through tracker, and plot the changes in kinetic, gravitational potential, spring potential, and total energies. The system for this lab is the mass, spring, and earth. There is no external work applied, so the change in total energy will be zero. Although Professor stated that the initial spring length L0 and spring constant K can be the same value as the EDX videos, I chose to calculate them myself because my position data would not be the exact same, which would result in false graphs. These calculations will be explained in more detail later on. The box on the right gives a general idea of the system in this lab. Using the legend, you can see that there are only two forces acting on the oscillating mass, assuming dissipative forces like drag and air resistance are negligible. The core concepts utilized in this lab are Newton's second law, the energy principle, the period of oscillation, and the relaxed spring length formula. The velocity update formula can be derived from the momentum principle as seen in previous labs. The energy principle for this lab states that delta E equals delta K, the change in kinetic energy, plus delta U sub G, the change in gravitational potential energy, plus delta U sub S, the change in spring potential energy. Because the object is initially at rest, its change in kinetic energy is given by 1/2 m times Vf squared. The gravitational and spring potential energies are given by mg delta y and 1/2 k s squared respectively, where s is the distance the spring was stretched. The spring constant can be calculated by solving for k in the equation T equals 2 pi times the square root of m over k. In this experiment, we are assuming the mass is beginning at rest, so the magnitudes of the forces of gravity and the spring are equal. Therefore, the initial length of the spring is equivalent to the magnitude of L minus mg over k. Now, looking at the tracker video, you can see that the mass is changing position in both the x and y axes. This means that there are two separate position versus time graphs, seen in the top right. All of this data will be saved in Excel as a CSV file and used to produce a visual model of the system. To find the period of oscillation for x and y, I found the time it took for 3 oscillations and then determined the average. The y oscillation period was used instead of the x oscillation period to calculate the spring constant value of 7.17 newtons per meter and the initial spring constant value of 0.151 meters for reasons that will be discussed in post-experiment analysis. For my code, you can see the given mass of 0.402 kilograms, the initial position determined by tracker, the initial velocity of 0, and the calculated spring constant and rest spring length on the left. Underneath these values are the equations for the stretched spring length and the different energies present. On the right, you can see the net force being composed of F grav and F spring. The velocity and position update formulas are implemented to change the ball's data as time goes on within the loop. Finally, the changes in energy are found so that an inclusive graph can be produced and analyzed. These are the two position versus time graphs produced by the code. The blue line is the model from tracker, and the red is the experimental data produced by GlowScript. As you can see, the lines are very similar, and the small discrepancies are most likely due to the presence of drag and air resistance, which were not accounted for in the experimental model. Here's my full GlowScript code, and if it's run, you can see the visual of the mass, spring, and earth system. The change in energy versus time graph you see below will be analyzed further in the next slide. To conclude whether or not the energy principle was satisfied, the delta E should equal 0 because no external work was applied to the system. Looking at the graph on the right, it is very clear that the change in different energies cancel out, and the change in total energy, or the orange line, is always 0. As a result, the energy principle for this lab is satisfied. So why did I use the y period of oscillation value instead of t sub x? The answer is because there is more motion on the y-axis than the x-axis, so the values of k and L0 present more accurate models of the changes in energy.